We already invented non-minus linearity. Take a number, run it through a simple bend, and suddenly straight lines can curve. Now we ask a sharper question. If we want a machine that maps inputs to outputs, and we only allow ourselves addition, multiplication, and one non-minus linear bend, what is the simplest, scalable blueprint we could build? Start with the smallest interesting component. Take inputs, multiply by weights, add a bias, then apply a non-minus linear bend. That is a neuron. It is not biology. It is a function you can write down. The bend is crucial. Without it, stacking more layers would collapse back into one linear map. A single neuron can only bend one straight boundary into one soft step. To get richer shapes, we build many neurons in parallel. Each one draws its own soft cut of the input space. Then we combine them with another weighted sum. This is the first neural network, a layer of bends feeding into an output. Here is the key conceptual leap. Each hidden neuron computes a soft half minus space. It turns on one side of a line, off on the other, but smoothly. The output then adds these soft regions together. So the network is not mysterious. It is a weighted mixture of simple geometric features learned from data. Now watch what happens when we add those hidden activations with positive and negative weights. Positive weight means add this soft region. Negative weight means subtract it. By stacking additions and subtractions, the output can carve out localized shapes, bumps, blobs, and curved decision boundaries, even though every hidden unit started from a straight line. So far, we built the structure, but not the learning. The network has many parameters, weights and biases in the first layer, plus weights and bias in the output. We already know how to learn parameters. Choose a loss, then follow the gradient downhill. The only new problem is computing the gradient efficiently for all parameters at once. The trick is just the chain rule, applied repeatedly. If you know how a later quantity changes, you can push that sensitivity backward through each operation. That gives gradients for the last layer, then the hidden layer, then all the way back to the first weights. This is backpropagation, but it is really bookkeeping for derivatives on a graph. Let's make one piece concrete. The hidden neuron output is sigma of z. If sigma is flat, its derivative is near zero and gradients die. If sigma is steep, gradients flow. This is why the choice of non-minus linearity is not decoration. It controls whether learning signals can pass through the network at all. Now we can finally name the invention. A neural network is a function built by composing layers, affine maps followed by a fixed non-minus linear bend, repeated. Learning is just adjusting the weights to reduce loss, using gradients computed by the chain rule on this layered structure. No step required faith. Every part is explicit and checkable. Next episode is about depth. One hidden layer already makes curved boundaries, so why stack many layers? The answer is not that deeper is more powerful in some vague sense. It is about reusing intermediate features, building complicated geometry from simpler geometry, and doing it with far fewer parameters than a shallow model would need.